Okay, this lecture is the first of a two-part series about neutron multiplicity counting. And this lecture is going to be principally experimental, practical, what I would call phenomenological, meaning here's how we do it, here's how the equipment works, here are the results, isn't it good? What's fundamentally lacking in that, obviously, is the conceptual framework. That is, why is it working? Why does it work well? What is the effect? And that will be the basic topic of the second lecture. And the second lecture, very simply, is going to be the derivation of the multiplicity point equations beginning to end, step by step. Now, what we will do actually here in this lecture is talk about a fair amount of mathematics. It's just not going to be the mathematics of the derivation. It's rather going to be some of the mathematics, for example, solving the equations. And I will finish this lecture with a conceptual framework of what multiplicity counting is and how it's derived conceptually. That is, I'm going to discuss conceptually what a probability generating function is, why we use it, and why, in fact, that is the way that multiplicity counting is derived, without actually doing the mathematics. But the reason for that is that there are some concepts that I want people to be comfortable with during this lecture that I always found when I studied multiplicity counting to be very strange, in fact, to be arbitrary, capricious. Why did you come up with this stuff? Who thought of it, and why did it happen that way? There was nobody that ever said, well, we did it because, and first we did A, and then we did B, and then we did C, and there was a progression. And that is really what we want to achieve here. But in order to do that, we've got to make you comfortable with some concepts of what they are, and then later on we'll see why they were choosing the way they are. So basically, I'm going to start with the phenomenological aspect and discuss the problem with multiplication in alpha when we do neutron-based assays. I should actually make another preface comment. This lecture is not a standalone lecture, and it's not intended to be. It is intended to be the follow-on on the previous lecture I gave on coincidence counting. And so I'm going to borrow from that and refer to it instantly. And so, in a sense, you've really got to be familiar with it. So, starting with coincidence counting that we talked about last time, the motivation for multiplicity counting is that there are problems. The motivation for multiplicity counting is that there are problems with coincidence counting. And those problems basically are associated with multiplication and are complicated actually with alpha and multiplication. There were some stopgap methods used in coincidence counting before multiplicity counting to address that, which are the known alpha and the known M method, and also the calibration curve, all of which basically are ad hoc methods to address the fundamental limitation of an unknown multiplication or an unknown alpha as long as unknown source mass. So I'm then going to move into a general explanation of what multiplicity counting is, show how you solve the multiplicity equations. Again, I'm going to stipulate those equations without deriving them. That'll be the subject of the next lecture. The design parameters for multiplicity counters, examples of multiplicity counters, lots of data comparisons showing how great multiplicity counting works, and then how the multiplicity shift register works mechanically. What is the actual mechanics of how a multiplicity shift register works? And then I'm going to finish with a conceptual framework, just conceptual, of what correlated factorial moments are, and more importantly, why we use factorial moments at all, which was one of the things that always confused me. Now, this is a slide modified from my coincidence lecture. We talked about previously in coincidence, the fundamental neutron measurement problem is that we had two sources of neutrons, one of which were alpha N neutrons, which occurred one at a time, and the other was fission neutrons that occurred on average about two at a time, but really sort of several at a time. We also talked about the emission distribution. And we talked about then the fact that how do we distinguish between an alpha N neutron, shown by this process, nucleus, alpha decay hitting a light nucleus giving us a neutron, and the fission process, just a fission, spontaneous fission here, giving us the sort of canonical two neutrons. Really, it's a distribution. How do we distinguish between the neutrons that are produced? They're identical neutrons, and they're detected as identical neutrons. Now I'm going to actually complicate that and say there's a third process now, which is the induced fission process, where either of these kinds of neutrons or these kinds of neutrons can in fact induce a fission and release more neutrons. And the time scale that this happens on, by the way, is such that it essentially happens instantaneously. which is to say it happens on time scale small compared to the detection time of the counter. Remember the die-away time. So if this causes this, and then one of these causes another one of this, all of that happens on time scales, time very short compared to the die-away time. And now we've got to distinguish between all three. Because if this is what we want to measure, this obviously looks like it. And I want to then just sort of belabor the point of induced fission. Induced fission is a process that gives us multiplication. It's really what is of interest. Fissionable material, what bombs and reactors are made of. And it depends on a lot of things. If you take the criticality safety course at the lab, you understand it depends on mass, density, geometry, for example, composition of the sample. And we talked in terms of the leakage multiplication, which is the multiplication that ultimately gets out of the sample and corrects for the fact that some of the multiplication in the multiplication chain has to be used to continue the multiplication. And T here is the global probability of basically a neutron inducing a fission. So, state the problem now. If we have a sample that has multiplication, i.e. there is a process other than spontaneous fission and other than alpha n, which is how we frame the coincidence counting problem, but now has, in addition to that, induced fission, which we then can parameterize by multiplication as a way of saying how much of it we have. Coincidence counting doesn't correct for that. And in particular, in all fairness, it really doesn't account for it when you've got multiplication and alpha n induced multiplication. And I want to make that qualification clear because, in point of fact, if there's what is known as the known alpha method in coincidence counting, when you can, in fact, do a correction. You could perhaps, if you have a set of samples that are all the same, you can do a calibration curve. But allow me here, without all the detailed qualifications, to say that there's no principled method for correcting for both an unknown alpha and an unknown multiplication. And the reason is simple, that only two pieces of information are used, the singles and doubles, which we call in coincidence counting the totals and reals. And this can induce large bias errors. So, for example, here's a calculation using the figure of merit code. This is honest to God true. I was surprised when I saw it. Here's the sample leakage multiplication and the percent error coincidence bias, and it's huge. And it's instantaneous. Multiplication is a big effect. Now, method one for doing that is a calibration curve. Notice the difference between this slide and the previous slide, I should have emphasized this more, is that the abscissa here is multiplication, which of course is typically associated with mass. In this case, it is the abscissa is actually, in this case, plutonium mass, and so the multiplication variation here is actually quite modest, which is why this change is somewhat modest. But the point is that you can see that the normal linear relationship that we associate with mass, again, recall the coincidence counting last time, is that the doubles rate or the reals rate was linear with mass. Clearly is no longer linear, and the departure from linearity is due to the multiplication effect. So one approach to that, admittedly ad hoc and limited, is to just simply do a calibration curve, a polynomial curve, for example, which this one is, and just simply calibrate to it. The problem with that is severalfold. Number one, you can only do this as interpolation. Calibration curves are only interpretatively valid. Secondly, you have to do this only for samples that basically have the same size, the same material type, the same pretty much everything except raw mass. Because otherwise those other variables will obviate the calibration curve. Now another approach, and I'm not going to go into the math for it here in this lecture because it is a coincidence counting approach, is to consider the known alpha method. And the known alpha method says, all right, if I know the alpha, if I'm going to stipulate that I know the alpha, let's say it's a low value, let's say it's middle, so it's 0 or 1, we can then say use the singles and doubles of coincidence counting, and we can in fact calculate the multiplication that way. And so what we're really showing is the uncorrected and the corrected versions. And so this works pretty well. But there's a stipulation to it. The stipulation is that you know the alpha. So you can correct for multiplication, over a limited range, provided you can state explicitly that the alpha is well known. Once the alpha varies, this breaks down, and it breaks down very, very quickly. It's very sensitive to that parameter. So the problem then is that given an unknown alpha and given a variation in multiplication, there's the potential for huge bias errors in the assay measurement. And that is the motivation for doing multiplicity counting, is that what we would like to be able to do is calculate explicitly now not only the mass, which is what we were looking at before, but also the multiplication and the alpha, and solve all three simultaneously. And the way that we do that basically is that we're going to extend coincidence counting, although it's actually a rather involved extension, from the simple concept of measuring the total neutrons and the real coincidences to measuring the total neutrons, which we call singles, the real coincidences, which we now call doubles, and also triple correlated moments, which are basically 3 neutrons at a time. And we do that with a variation of the shift register. And what I wanted to do here is talk a little bit about terminology, again connecting back to coincidence counting. And I've already sort of said this, but when we used to talk about totals and reals and coincidence counting, we now talk about singles and doubles, and of course the triples are added onto that. The other thing that goes well beyond what we did in coincidence counting is that we're now going to talk about multiplicity distributions. And we need to understand that, and we'll talk about that at length. But let me first start us off again with one of the plots that I showed from the coincidence counting lecture. And remember the shift register approach. Again, I'm not going to go through all of that because from that lecture, we got, when we did the entire shift register approach, we got this kind of a histogram, which is the modified or the perturbed Rossi alpha distribution, where the green represented the correlated neutrons that we would see by the shift register due to fissions. And what those referred to is that these were the neutrons that were the second of the 2 canonical neutrons from a fission when we were aligned on the first one. And we talked about the fact that in the coincidence lectures that in fact the green were not a measure of neutrons. They're actually a measure of coincidences, and we did that. But just as the green is a measure of coincidences, if you think about it, they could also included in that be a measure of the triples or even higher order moments. Because what we're really measuring is the ways that you count neutrons at the same time. So let's go and talk about that. Remember again, this is a modified slide from the neutron coincidence lecture. And we consider a number of events, let's say they're neutron counting pulses, within a particular time window. So I'm defining a time window. That time window, by the way, can be arbitrarily small. In the case of an actual fission, it can be essentially instantaneous. But let's, the common way of thinking of it is within the detection window of our shift register electronics. And we see here we go back and connect to our coincidence lecture. If we have a single neutron, we obviously have 0 coincidences. If we have 2 neutrons, we have 1 coincidence. And I should actually talk about the default case, the trivial case. If you have 0 neutrons, you also have 0 coincidences. If you have 3 neutrons, you have 3 coincidences, and I show them here, this with this with this, and that with that. And then if you have 4 neutrons, you have 6 coincidences. And we can do the same kind of analysis by looking at 3 correlated events, or triples, basically. That is, how many ways can we get 3 things taken at a time? And actually, it's the same formula. It's a combination formula, but obviously it's 0 in that case, 0 in that case, and with 3 is the first time that we actually get a triple. In the case of having 4 neutrons, there are actually 4 triples there, because there are 4 ways, 4 combinations of taking those 4 neutrons 3 at a time, which is the combination formula. So I want to get a sense of the generalization from coincidence counting to multiplicity counting is the addition of the triples, and the concept is identical. We use the same basic concept, the combination formula straight out of basic probability and statistics, of how many ways can you select so many things at a time from a number of items. And following again, let's consider again, this time, how we would actually apply that in the case of an actual fission event. Again, taking from the coincidence counting lecture, we talked about the fact that in a real fission, in this case I'm taking a spontaneous fission for plutonium, you get a distribution of neutrons emitted when that fission occurs. And so you can actually, when a fission occurs, you can have 0, 1, 2, all the way to 6 neutrons emitted at that instant of time. And of course I can define that as within a time window. And this defines the probability distribution of getting that many neutrons emitted at that instant of time during that one fission. And there are similar distributions for induced fissions and for other isotopes. Indeed, I will point out that the profile or the distribution for induced fission actually goes all the way up to 8 neutrons at a time, and also sort of a similarly shaped distribution profile. Now again, connecting back to the way we did it in coincidence counting, we said, all right, since we can have several neutrons emitted by a single fission, how many coincidences will that correspond to? And we basically say, well, again, if it's 0 neutrons, it's 0. If it's 1, it's 0. If it's 2, previous slide is 1. 3 gives us 3. 4 gives us 6, and so forth. And that comes from the simple formula here shown as basically the combination formula, which, by the way, is nu factorial nu minus divided by nu minus k factorial k over k factorial. In the case of k being two things taken at a time, that simply reduces to nu minus 1 over 2. In the case of triples, that would reduce to nu minus 1 times nu minus 2 over 6. Again, the same formula being used. And to get the actual number, all we simply do is take the expectation value of this by summing, in this case I say integrating, but summing over this probability distribution. And the point I'm trying to make here is that we can apply the same formalism I showed here for coincidence counting to triples counting. It's just that instead of taking 2 things at a time, we now take 3 things at a time. We use the same formula, that is the combination formula, and we use the same mathematics of taking the expectation value, which is integrating with the distribution function. Here's another slide saying essentially what I just explained. So basically for coincidences, we do nu minus 1 over 2. For triples, it's nu minus this formula, and it's basically the combination formula. Okay. Alrighty. So I wanted to make the connection So where am I? We wanted to say that we want to measure more than we can with just coincidences and singles, because we need to measure 3 things. And we also wanted to make the connection back to coincidence counting, that we can actually count triples because we can use the just basic combination formula from probability and statistics, and we can take the expectation value of that probability just like we would by integrating or summing of the distribution function. Okay, so let's sort of summarize and see where we're going here. We have spontaneous fissions, alpha and neutrons, and induced fissions, and they have different neutron distributions. That gives us more information in the pulse train, and we want to extract it. The coincidence counter measures the totals and the number of reals, which we talked about in the coincidence lecture. What we're going to do in a multiplicity counting is to get the number of totals, which are singles, the number of pairs or coincidences or reals, which are doubles, and also the numbers of triples. And the way that we're going to have to do that is that there's not going to be the simple mechanism that we talked about before. This becomes a lot more complicated because now we need the multiplicity distribution itself. It's the only way to do it practically. And then from that multiplicity distribution, we will then calculate the number of singles, doubles, and triples. When we get the number of singles, doubles, and triples, we can then solve using the point model equations. And by the way, I know that I'm sort of just, this is very phenomenological. I'm just telling you what we're going to do. We'll come back and explain the details of that. But I want to give an overview. So, the overview is we need a third piece of information. We needed to get mass multiplication in alpha. We know that we can get triples because that's a natural extension using the combination formula to coincidence counting. Once we have singles, doubles, and triples from the point model equations, which we'll derive in the next lecture, we can then use these equations by inverting them to solve for mass multiplication in alpha. But these are now in the non-inverted form, where it basically says that, for example, the singles is equal to the fission rate times the efficiency times the multiplication times the expectation, the first moment of the factorial distribution of an actual fission event, which is actually the expectation value of the number of neutrons emitted per fission, times 1 plus alpha, where alpha is the ratio of alpha n neutrons to fission neutrons. So you can actually, and we're actually going to go through that and dissect it. I'll show it in a second. Similarly, we have an equation for the doubles, or the coincidences, and then we have an equation for the triples. So those are the neutron multiplicity equations. Now, what I want to do is deconstruct this and show where it comes from, somewhat again phenomenologically. This is not as rigorous as doing the actual derivation with probability generating functions, but it illustrates where the equation comes from. So we take that first singles equation, we can do this for all of them, by the way, and we break it out term by term. We factor it out. And I think you can see, I should show this again. What I've done here, basically, is I've taken the multiplication and I've changed it to m minus 1, and then I've reintroduced the term back. And it just makes it very easy to understand. So now, we have each term. Here's f0 m e nu s1. Here's the same thing times m minus 1. Those two together are just simply fe m e nu s minus 1 times m. I split it out because they're actually separate processes. Did the same thing with the including the alpha term as well. And you'll excuse me, that should be a capital M. If you then take a look at these term by term, this first term are those total neutrons that you get from spontaneous fission. The second term are those total neutrons that you get from induced fission, where the induced fission was caused by a spontaneous fission neutron. The third term are those neutrons that are caused by alpha n neutrons. And the fourth term are those neutrons caused by an induced fission when the induced fission was caused by an alpha n neutron this time. So you've considered all four possible processes, and then just simply by simplifying the algebra, you get the standard equation for singles, which is just this one here. Similarly, and I'm going to try this a little bit of a different way, we can relate the doubles equation that I just showed you there before to the coincidence equation for reals that we derived in the previous lecture. These are just copied from those two sources. And we can just do a term-by-term comparison, which I've done here. And you see that this matches term by term. And what happens then is that the difference is very clearly that if you take m equals to 1, this whole term disappears, that becomes unity, and those two equations become the same thing. So when we talk about the coincidence equation that we derived the last time, we implicitly assumed, I didn't talk about it then, but we implicitly assumed that there was no multiplication. We didn't talk about induced fissions. There weren't any. That's the whole point of this lecture. So we talked about strictly spontaneous fissions and alpha n fissions. There weren't any induced fissions, and we were able to derive term by term this equation. What I'm trying to show now is that you get the doubles equation now reduces to the same thing when you again assume that there's no multiplication. If you add multiplication, you get significantly more doubles, and those are the terms that are represented here. And so what that equation basically says, and I'm sort of repeating myself here again, this is another way of saying the same thing, is that just as we derive the multiple sources of doubles, no, I'm sorry, let me try that again. There are multiple individual sources of the single neutrons for the single equations. And we're going to do essentially the same concept here. That is, let me go back and try to show this. When we went back to the singles equation, we said we get some single neutrons, individual neutrons, from spontaneous fissions. It also produces coincidences, but it also produces neutrons. So you get single neutrons from spontaneous fissions. You get single the neutrons from the induced fissions, where the induced fission is caused by a spontaneous fission neutron. You get alpha n neutrons and you get alpha n neutrons caused, no, you get neutrons from the induced fissions when the induced fission is caused by alpha n neutrons. And the same thing applies to the doubles, except now we don't get any doubles from alpha n neutrons at all, because alpha n's never produce doubles, they always produce them one at a time. So what happens is that we only get doubles from spontaneous fissions. Remember, that was the whole point of coincidence counting. Coincidence counting, the green, coincidences or reals, was specific to fissions. So you're not going to see anything from alpha n's here. So you get coincidences or doubles from spontaneous fissions. But you also get doubles from the induced fissions when the cause was the spontaneous fission neutron. See the pattern? It's repeating. You also get doubles from the induced fission when the induced fission is caused by an alpha n neutron. Same pattern, same approach. And again, you can build this up from it. This is a rather hand-waving phenomenological description of these equations. And in the next lecture, we will actually derive them mathematically. What I wanted to achieve here was a sense of comfort, a sense of intuition of where these equations come from. That is, the singles equation comes from various different physical processes which we can identify. Same with the doubles equation, the triples equation, I'm not going to try it for you. But the point is that we can sense that these equations come from the natural physical processes of alpha n, spontaneous fission, and then induced fission. When we consider all this, the induced fission is thought to occur essentially simultaneously with whatever neutron process created the neutron that caused the induced fission. That is, do not think of sequence. Think of it as simultaneous. When the alpha n, let's say, decays and gives us a neutron that causes causes an induced fission, the alpha n decay, the alpha impinging on a light nucleus causing us to get a neutron, and then that neutron impinging on yet another nucleus to give us an induced fission. From our point of view, all occurs simultaneously. It's singular in time. Or more precisely, it occurs on time scale short compared to the detection time of the detector. Okay. So these are the equations that we can now invert once we know singles, doubles, and triples to get mass multiplication in alpha, with just a little bit of phenomenological explanation of why they are there. I'm not comfortable with that. Now, let's talk about how we actually get singles, doubles, and triples. First, let's go back and talk about what we talked about in the coincidence counting lecture. This was again taken from the coincidence counting lecture, and we talked about how the shift register worked, and I'm not going to go through that except basically to say what the results are. In the shift register time, that is the time that a neutron enters, the time that it leaves, defines the gate time. It's the length of time for the gate. The up-down counter is just simply the mechanism that keeps track of how many neutrons are in the shift register at any time. And then this is strobe so that we get the R plus A, the reals plus accidentals, when we get a new neutron, and then after a long delay we get the accidental scalar. And the whole idea is that this thing is aligned such that the R plus A scalar is timed to get the green. Try to go back here and find that. I know I said I wouldn't do this, but I'm going to do it anyway. The R plus A scalar looks at this time here, and then the subsequent A scalar looks at this time here, and the whole point of it was to get the green. We talked about it last time, but that's how that works. Now, again, just simply looking at the total number of strobes that we get and keeping track of that is the number of total counts. So we get singles and doubles, or we get totals and reals, which is fine, from the shift register. The question is, how do we modify this to get multiplicity? And the answer is actually very significant. Just to get the triples, we have to completely redo the shift register. So I'm going to walk us through that, because the output of this is not just simply the R plus A and then the A coincidences. It is, in fact, the multiplicity distribution. Again, we have an input. We have a pre-delay. The pre-delay is a pulse pileup issue, but I always like to think of it as it allows you to strobe the scalars before the neutron gets onto the escalator. Again, we have a shift register that establishes the time window, or the time gate, that we have a neutron, basically, that we're looking at. The up-down counter keeps track of how many neutrons are on the escalator at any one time. And now the next thing that we do, at this point in time, we would actually add this number to the scalar. So if there were 50 in the up-down counter, we would add 50. If there were 5 in the up-down counter, we would add 5, and so forth. But we would add this number. We don't do that anymore. Instead, we sort by the number in this counter, actually between 0 and 255. 256 possibilities, because that's digital logic, and that's in 2 to the 32nd power, I think. 2 to the, no, that's wrong. Anyway, it's a power of 2. And we now sort, and we have actually 256 separate scalars. So that if we have a 0 in this counter, we actually sort and get a 0 selected for the 0 scalar. If we have a 1, we go to the 1 scalar, and 2, we go to the 2 scalar. So that now every time we strove, we simply count the number of instances, the number of cases where we had a 0 in here, or a 1 in here, or a 2 in here. So we don't add the 1, 2, or 3, or 5, or 256, or 255, as high as it goes. We simply note that we had 255, or 100, or 15, or 1, or 2, and add that case as a single. So this, if we had 0 in here, we would increase this by 1. If we had 1 in here, we would increase this by 1. If we had 2 in here, we would increase this by 1, and so forth. So what we get is the number of cases or incidences where we had so many neutrons on the shift register when a strobe came in. And then we do the long delay, and we repeat the whole process for the accidental scalar. So we have basically a scalar for the R plus A, 256 of them actually, and then 256 accidental scalars as well. And we do that process, and what we get out would not be too surprising. This is the first 64 for a particular distribution measuring for a particular time, where we have that R plus A zeros scalar, and then the accidental 0 scalar, then the 1 scalar, the 2 scalars, the 3 scalars. And these numbers represent the number of times that the system had received a strobe when there was 0 counts in the shift register. And this is the number of times that there was 1 count, the number of times there was 2 counts, the numbers of 3. And this is a multiplicity distribution. That is, and I should define it, and actually do define it formally, but it is the histogram, or the likelihood, or in this case it's the number of cases, where you had a particular number of multiplicity, namely number of neutrons in a particular time window at an instant when you trigger it. And I can plot that up as a histogram, and it looks like this. And that's just simply the same case plotted up. I don't think I did all out to 64 or 256, but it shows both the reals and the accidental scalars there. And this neutron distribution is conceptually identical to this one here. They are the same. This is the probability, or the number of cases, same thing, where you have 0 neutrons, 1 neutron, 2, and so forth up to 6, or for induced neutrons, induced fissions up to 8. These are the likelihoods that you'll get there. These are the likelihoods that you'll get 0 neutrons, 1 neutron. But you can normalize this and turn it into a probability distribution. So these two things are the same. They are multiplicity distributions. They are the probabilities that you get a certain number of neutrons in a certain size time window, whatever time window you decide to select for a particular case. And so just as we used the counting formula should we put my slide back? Just as we used the counting formula to count coincidences in the case of a singular fission, or modify this to count triples in the case of a singular fission, we can do the same thing for this. Same formula, same approach. Everything is the same in that regard. And we can get other distributions. Here's a case for americium lithium. It looks a lot different. Why? Because there are no fissions in americium lithium. This is a log plot, by the way. It's all totals. And the reals and the accidentals are the same for the singles because the accidentals for the singles is a meaningless quantity. Point is that you have no reals of any kind because this does not produce any reals. That's why it's an Embry-Symmetric source. It's a single source. And here we can do the same thing for a Californium source, which is only spontaneously fissioning and gives you no induced fissions at all. And again, we have this distribution of instances for this measurement time, and of course you can just normalize this into a probability distribution of when you get certain numbers of neutrons in a particular window. All right. What do these things mean, and what do we do with them? And I think I've sort of answered this in terms of what they mean. What they really are is the number of cases. This is how they are the multiplicity distributions. They differ from that multiplicity distribution of the singular fission only in that this is a slightly longer count time, and this is the detected rather than the emitted. This is the detected from a whole sample rather than the emitted from a single fission or a single nucleus. But other than that, they're conceptually the same. Now, just some sort of phenomenological observations. The higher the count rate, the more that this thing will shift out. To explain that conceptually is that, remember in the coincidence lecture when we talked about the accidentals totals correlation, the fact that the accidentals rate for coincidence counting was G times the totals rate squared. And I explained that sort of phenomenologically by saying as the totals rate increases, the number of rulers that you use increases, but the density of neutrons inside the counting gate also has to increase. That's just common sense. Higher counting rate, higher number of neutrons per unit time, any unit time. We typically think of neutrons per second, but equally I could say neutrons per gate time. Therefore, if you increase the number of neutron rate, you're increasing the neutrons per gate time, which means that there are more neutrons in the gate, meaning this whole distribution is going to move up. But the real multiplicity information, which is the reals plus the triples, is represented as the difference between the reals plus accidentals and the accidentals element along all of these. So the total distribution of mass depends on the singles or the count rate, but the reals and the triples depend on the difference between the reals plus accidentals and the accidentals components for each one of these, because remember there are two plotted here for each case. That's common sense. The reals was dependent on the reals plus accidentals minus the accidentals. That's in the coincidence lecture. Same thing is going to apply here. Okay. So now that we have this nice distribution, and we have sort of an intuitive sense, I hope, of what it means, how do I actually convert it into something that I can use? And the idea is to reduce it to singles, doubles, and triples, and just by direct analogy to how we measured coincidences and triples in the case of a single fission, we use the combination formula to calculate this. And so let's just do that. Here's the combination formula for the thing taken, n things taken one at a time. You just simply sum over the number of total accidentals you've got. Q, by the way, the Qn is the accidentals and Pn is the reals plus accidentals. But you just simply sum over. The doubles now, following the formula, is equal to n times P of n minus the accidentals. We're doing the same thing as we did before. Now you'll notice this formula differs from the one I showed before. You should say, wait a minute, it wasn't n P of n, it was n minus 1 P of n, or nu minus 1, it doesn't matter. What's the difference? And the difference is, remember, is that for each n, that is the case number. So if we're looking at case number 5, that means we have the case of 5 neutrons in the gate. And therefore, we get the extra nu by the fact that it's the case number. That is, when we add all these things up, I'll try to say this to make sure. P of n is the probability that we will have n neutrons in there. So that should actually count as if let's say n is 5. It should count as 5. We have 5 neutrons there, but we only get 1 in the count. So that's why we get the extra factor. And in the case of triples, it's a lot more complicated. We now have the next term. And we have this cross-correlation term here. That is, if you look at this, this is again now the next term in the moment distribution, n now times n minus 1. By the previous formula, it would have been n minus 1, n minus 2. But I've explained we take up the factor because we add the number of cases. And we subtract out the accidentals here using the same formula. But then we have these things here, which are the reals. And I'm going to do this phenomenologically again because the math of this will be done in the second lecture. Consider the original coincidence problem. And I actually may have, I will talk about it a little bit later again too. The original coincidence problem said, how do I tell the difference between two alpha n neutrons where the alpha n decay just happened by accident, hence the name accidental, accidentally occurred at the same time producing two neutrons at the same time that I detected at the same time. How do I distinguish that case from the case where I had a single fission, which produces the canonical two neutrons in the simplified model at the same time and were detected at the same time? Two different cases, two neutrons produced at the same time, two detected at the same time, they're identical. We have a now somewhat analogous but more complicated problem here. How do I detect the difference between three occurring at the same time? Let's say we now have either fission or a fission chain that produces three neutrons at once. How do I tell the difference if that's an honest-to-God three-neutron event? Let's say a spontaneous fission where three neutrons were occurred. Let's say an alpha n inducing a fission of two neutrons, because that's still an honest-to-God triple, because of the causal relationship, producing three neutrons at a time. So how do I tell the difference between a case where I have an honest-to-God three neutrons produced at once from the case when I had, by accident, an alpha n neutron producing 1 and a separate spontaneous fission producing 2. 2 plus 1, different events which occur accidentally. But they still give me three neutrons at the same time. How do I tell the difference between the two? The answer is, again, of course, I can't on a neutron-by-neutron basis. But what I can do is say, all right, I know what my doubles rate are, I know what my singles rates are, and then from probabilistic considerations, I can calculate how many times I'm going to get the fissions occurring at the same time with an alpha n, such that that will look like a triple but isn't, and that's how these terms are calculated here. And you have the P of n because that's the R plus A, but remember I've got to get the real fissions that occurred, not just the R plus A, so I've got to subtract out the accidentals and the reals, and that's what this is.
If you were using quads, you'd have terms
for the triples and the doubles, because now I'd have to worry about how do I tell about, is that two fissions occurring separately? How about a triple plus 1? Yeah, it's a lot more complicated, but exactly right. Same principle would apply. You need to correct. So that's one of the reasons that the quads uncertainty is so high, and you can see even why the triples uncertainty is so high. I have the uncertainty in the foreground distribution, the uncertainty in the background, reals plus accidentals and accidentals. But I got to add into that the uncertainty of the coincidence counting, the doubles distribution as well. Quads, then I would have to add all three. So that's how we take. So now I've shown the shift register. We've shown how the shift register gives us a distribution which we call a multiplicity distribution. It's a probability distribution of the likelihood of events with 0 to 255 neutrons in a time window. We've shown how we actually calculate that using the same combination formula to get the singles, doubles, and triples. And now we're back to the multiplicity equations, which tells us from the basic physics parameters, the spontaneous fission mass, the multiplication, and the alpha, which appear in all these terms, and then a bunch of constants, physics constants. For example, the multiplicity distributions of individual events, which is the multiplicity moments. Remember, taking the multiplicity distribution of a single spontaneous fission or a single induced fission, we can calculate first, second, and third factorial moments, and those are nuclear constants, and also then the parameters such as the efficiency and the gate time of the detector. And we can invert those equations, and I'm not going to go through the math, I'm simply going to state the results, is that in order to solve for the multiplication, so we're going to solve, given a known efficiency for mass multiplication in alpha, we actually have to solve this cubic equation, which involves the parameters of singles, doubles, and triples to get the multiplication. And to solve that for the multiplication, you can then substitute it back in to get the mass and the alpha. And similarly, you can do the same thing, where in this case, I actually assume that multiplication is 1. I'm getting a little bit off the subject. And now I can actually solve for the efficiency of the detector. This is an application which you might use for waste applications when you have a lot of matrix materials, a lot of attenuation of the neutrons, and you want to do that. You can solve the same equations that way as well. So now, I want to go into the next aspect, which is starting to consider the design of multiplicity counters and what they might look like. John brought up a point wonderfully which led into this, which is the fact that because the triples depends on the doubles, you get the error in the triples, which actually is normally worse precision anyways because there are fewer triples normally, plus the error in the doubles. And therefore, you get higher errors, higher precisions, worse precisions with multiplicity counting than you would for coincidence counting. So what I've shown here is the following simple case using the figure of merit, Robert Enslin's figure of merit code, where I'm talking about percent error. This is just precision. I'm talking sample mass in grams. I'm allowing a little bit of multiplication to vary here from 1 to about 1.1. Alpha is equal to 1, sort of nominal garden variety coincidence counter, 25% efficient. And we take a look at the precision, and we see that the doubles precision dies out pretty much as we would expect, but it does flatten out here. And by the way, if there were no multiplication, it actually starts to curve down here. If there were no multiplication, it would be flat here. If I were to actually plot the singles I did on this case, it would just go down monotonically as 1 over root n. This is a log-log plot, so it would come down monotonically as 1 over root n. So I need to talk about this a little bit. Again, we discussed this in the coincidence counting lecture, and I want to talk about it here again to explain this behavior. In the coincidence counting lecture, I pointed out that the singles goes down because the relative uncertainty goes down as 1 over the square root of n, because it's a Poisson process. Since I described that at length then, I'm not going to go into it now. The doubles, however, actually has 2 areas of concern that we would actually evaluate. The doubles uncertainty, you can actually do it in one regime or another. And you get sort of monotonic decrease going down as 1 over root n, followed by no improvement in precision whatsoever, even with higher count rates. And the reason for that is simple. The uncertainty in doubles is not only the reals plus accidentals contribution, but it's the accidentals contribution as well. And the accidentals rate is proportional to the totals rate squared. We talked about that in the coincidence lecture, and I went through it in detail. Now that's important, the fact that it goes as the singles rate squared, or the totals rate squared, because for low values of mass and low count rates, the contribution of the accidentals uncertainty is small relative to the uncertainty in the actual number of doubles. And so your doubles decreases as 1 over root n because you get better counting statistics following normal Poisson process. All right, I went through that. And then when you get into higher count rates, now the accidentals dominates the error term, because the accidentals has gone as the total squared, so now it's the big term, and the number of totals is the negligible term, and the 2 cancel out, and you now get basically no improvement at all. In the case of triples and multiplicity counting, and I've shown the triples error and the multiplicity error and the triples error here, it actually turns around and gets worse by the same concept. Is that now, because of the much increase in the accidentals, which now doesn't go as the total squared, but the total cubed, it actually gets worse. As well as you pick up the error from the doubles as well. So it gets much worse very fast. And so the problem with multiplicity counting fundamentally, or the general measurement dichotomy, is this. We used multiplicity counting to solve the problem of uncertain multiplication or varying multiplication with uncertain alpha, which typically occurs at high mass because that's when multiplication occurs. And here's where we get burned, because in that same regime, multiplicity precision actually degrades. So one of the things that we have to balance is the degradation in bias that you get with coincidence counting versus the degradation in precision that you get with coincidence counting, or with multiplicity counting. They have to be balanced and considered. The approach that we've taken then is to consider regimes of operation and see which one works the best. Typically in very low values, coincidence counting works best. The multiplicity precision is very poor. In these regions in here, multiplicity counting clearly works the better. When you get up into here, when you get up to very high values, we start to find limits in multiplicity counting again. And the idea is to try to extend the region of multiplicity counting of reasonable precision. And that goes into multiplicity counting design. And again, what I'm taking for nominal sets of conditions, I think I'm taking 10 kilograms of material here and just nominal counting, nominal cases. Again, we're showing the percent error, which in this case is the precision. We're looking at the multiplicity error, the doubles error, and the triples error. Multiplicity precision includes both singles, doubles, and triples error included through the point model equations. What you see is you increase efficiency, all of these get better. And similarly, if I were to do this, all of these get better if you decrease the die away time, because you can shorten the gate, therefore shorten the amount of contribution from accidentals. So the answer is very, very simple. That when you design multiplicity counters, you want them high efficient and low die away time. And it's just simply to extend, fundamentally, to extend the region where multiplicity counting works, and also to improve multiplicity precision all across measurement values of interest. So if we start with our conventional high-level neutron coincidence counter, the HLNZ2, this is sort of a cross-section of a cartoon. You see that it has efficiency of 17.5%, die away time of 43 microseconds. And the point I'm trying to make here is that as we start to go with more modern counters, the efficiency starts going up. Die away time tends to stay the same or get a little bit less, but the important parameter, the strong one, is the efficiency goes up. And then continuing the implant pyrochemical neutron multiplicity counter now, the efficiency is 57.7%. This is the passive counter. So consider the difference between this one and the high-level neutron coincidence counter, which was 17%. This is essentially a little over 3 times the efficiency. The die away time is about the same. And I've just run out of slides, so let's take a 5-minute break here, and I'll get the next 20 slides and I'll be back.